Okay, so here it will be the screencast for the lesson that we had in the lab because it was a bit messy. So here are the physical properties of carboxylic acids. Note that their state at room temperature is also a liquid state, same as alcohol. But if we were to compare their melting and boiling point here, they are higher than alcohols. So why is that so? And also note that their solubility in water is very soluble. Okay. So as molecular size increase, melting and boiling point should increase, whereas solubility and strength of an acid will decrease. Now you do not need to know exactly why this decrease, you just need to know that it does. Okay, solubility will explain both melting and boiling point as well as solubility. So first, this part is the part that we've been talking about for all the homologous series. So as molecular mass increase, melting boiling point increase because the surface area increases. When the Wahl's forces become stronger, more energy is required, then there's higher melting and boiling point. Next, when it's more branched, it becomes a more spherical shape, and that will lead to lower surface area, weaker van der Waals, less energy, hence lower melting boiling point. Okay, if we compare carboxylic acids to their corresponding alcohol, we know that the melting and boiling point of carboxylic acids are higher. That's because of the presence of both the hydroxyl group as well as the carbonyl group. Okay, so remember that alcohol they only have one hydroxyl group. Okay, alcohol they have one OH group. Carboxylic acid they have C double bond O group. They also have the OH group. Okay, so based on that, you can see that there will be more hydrogen bonds formed between carboxylic acid molecules as compared to alcohol molecules. Okay, so this is the diagram that was drawn in class. Okay, note that because this is the slightly positive end of the hydrogen, and then this oxygen has what we call lone pairs of electron. Okay, why is it that it has lone pairs? Note that it used up 2 electrons in the bonding with carbon, right? So there are 4 more electrons that's not used, and these 4 electrons are being paired up actually in their orbitals. So this relates to your SPDF orbital model, where they are actually in these fixed orbitals, and because of the alignment of the orbitals, it can interact and form hydrogen bonds. So this is hydrogen bonding. Okay, if you were to define it, in JC you will learn the actual definition. In secondary school we don't test you on the actual definition, but the definition is hydrogen bonding takes place between an electronegative element that has lone pairs of electron with a hydrogen that is bonded to nitrogen, oxygen, or fluorine. Okay, these 3 being highly electronegative. So why must it be to a highly electronegative element? Because if hydrogen is bonded to a highly electronegative element, the electronegative element will pull the bonding electrons towards itself, making hydrogen slightly positive. And because it's slightly positive, it can interact with the negative lone pair of the electron or some other electronegative element. So that's why here there is hydrogen bonding. This slightly positive, this one there's lone pair. Okay. So in the case of a alcohol, Okay, there's only one hydrogen bond being formed. So that is why here there's two hydrogen bonds, whereas for alcohol there's only one. Okay, so recall this like dissolve like rule. Remember that polar molecules can be dissolved in polar solvents and non-polar molecules can be dissolved in non-polar solvents. So an example was that ionic compounds can be dissolved in water, alcohol can be dissolved in water because of the polar OH group. So why is it that carboxylic acids are soluble in water? It is because the hydroxyl group and carbonyl group enables three hydrogen bonds to be formed with water molecules. And the formation of these bonds is an exothermic reaction. Okay, why is it that solubility decreases as molecular size increases? The reason is the same as the one for alcohol. It is that because when the length of the carbon chain increases, the polar carbonyl and hydroxyl group becomes a smaller part of the molecule, and the molecule becomes more and more like a hydrocarbon. For instance, if I were to draw a long chain here with a carboxylic acid at the end, only this part is polar. This whole region is non-polar. Okay, so you will see that as the chain increases the length, the non-polar section becomes bigger and bigger, polar sections become smaller and smaller, so it is harder for a polar solvent to dissolve this compound that is actually more non-polar. Okay, so they are generally more soluble than their corresponding alcohol. So where did the three hydrogen bonds come from? Okay, so first, the carbonyl oxygen can bond with the hydrogen of the water molecule. Next, the oxygen of the alcohol group, hydroxyl group, can also bond with the hydrogen of a water molecule. Lastly, we have the hydrogen of the carboxylic of the hydroxyl group being able to interact with the oxygen of the water molecule. Okay, so you can draw this diagram to note that what are the three hydrogen bonds that can be formed when carboxylic acid is in water. Okay, next, production of carboxylic acid by oxidation of alcohol. Okay, there's another reason why carboxylic acids are also soluble in water. It's because remember that carboxylic acids in water, they can dissociate to form ions. So once they form ions, they are a lot more soluble in water. Okay, because there's a definite charge and they are definitely like a polar molecule. Once you have a charge, you are actually at one extreme end of being a polar molecule. Okay, so the production of carboxylic acid by oxidation of alcohol, this is what we learned in the previous lesson. So we can oxidize the alcohol to carboxylic acid with water. Some examples of oxidizing agents are acidified KMNO4, acidified K2Cr2O7. So there are three reactions of carboxylic acids: acid reaction, combustion, esterification. Now for the first one, we have actually learned something like that in Sec 2, and then for combustion, it's been the same all along. So that's why I didn't cover it in detail during the lesson. Okay, so there are three general chemical reactions of an acid: acid metal, salt, hydrogen gas; acid carbonate, salt, water, carbon dioxide; acid base, salt, and water. Okay, try and write this equation on your own. Okay, maybe to help you, I'll get you started on the first one. Ethanoic acid, you must know, is CH3COOH plus magnesium. This will give us magnesium ethanoate. So how do I write the formula? Now, there's two ways you can write magnesium ethanoate. You can either write the magnesium cation in front. Magnesium is 2 plus, CH3CO minus is only 1 negative, so I need 2 of it to balance. Okay, so this is the balance equation. Now you can also write this in this manner. Both are accepted because now this first method, follows the cation before anion rule. Okay, this second method, why is this also correct even though the cation is at the back, is because remember that a salt is when the hydrogen of an acid is replaced by a metal cation or an ammonium ion. So note that the acid H plus of COOH is at the end of CH3COOH. So when the metal cations replace the hydrogen ion, they are replacing it at the end. So that's why we write it at the end also. So both ways will work. So can you try the other questions yourself? Next, when carboxylic acids are combusted, they also give carbon dioxide and water as the only product if it's a complete combustion. Okay, let me give you an example. How many carbons are there? We have 2. So I need to have 2 carbon dioxide. How many hydrogens do I have on the left? I have 4, which means that on the right hand side I must have 2 water. Okay, totally up, I have how many oxygen? On the right hand side I have 6. I have 6. On the left hand side I have 4 already. To make it 6, I just need times 2 here. Okay, so incomplete combustion is similar. It's just that carbon monoxide or carbon is the product instead of carbon dioxide. So I think you can write those equations on your own as well. Let's move on to esterification. It is also known as a condensation reaction. Okay, carboxylic acids react with alcohol to give a sweet-smelling ester. The type of reaction is condensation. So how does this happen? Let me draw it out. Carboxylic acid, let's say I use ethanoic acid again. Okay, let me change color. Let's say my alcohol is, use a simple one lah, huh? Let's say I just use methanol. Okay, together, what is the ester that they are forming? We still have the carboxylic acid portion up till the carbonyl group. Okay, but note that this oxygen is from the alcohol. There are 2 possibilities, right? One possibility is that this oxygen here is the one from here. Okay, or it can be the one from here, from the alcohol group. So which is the one that's correct? It is actually from the alcohol group. To know why this is so, you have to know the mechanism behind this reaction. Okay, it is actually that the oxygen of this alcohol group, this oxygen, the lone pair, attacks the carbonyl center and forces this group to leave as water. Wait. Let me just, oh, that was cool. I didn't know that I can do that. There's an OH here, right? Okay. Now, you don't need to know the mechanism in detail. So what you need to do is, you just need to know where the bonds are from. So what do you need to know is you just need to know where that particular oxygen is from, because a lot of students mix it out and they think that it's just from the acid, and then I'm just adding the CH3 group from the alcohol to the ester. Okay, that's not the case. Let me just write down plus this gives me this plus that. Okay, so carboxylic acid plus alcohol give me an ester. Now how do I name this ester? Okay, or maybe I want to explain the word about reflux again. So this word reflux means that it is actually in this apparatus, like this flask lah. When this is your reaction mixture, what happens is we are heating it up and then it will vaporize, right? And then it will come back down. Because this is a long tube, So it vaporizes, goes up, then it gets condensed, and then it comes back down. So it's like keep boiling and condensing. So the temperature is actually kept at the boiling point. Okay, it's actually quite high. So we want the reaction to proceed at as high a temperature as possible. Okay, when we want to do things in reflux, it means we want them to really go to completion. Okay, how do we name an alcohol? First, you must be able to spot which part is the acid and which part is the alcohol. Okay, so how do you spot that? Remember, you see this C double bond O. Okay, this C double bond O must be from the acid. Okay, and what you need to remember is this bond here is a new bond. Okay, so here it will be my acid group, here will be my alcohol. Okay, so what is the first part of the ester comes from the alcohol. So from this part, how many carbons do I have? I have 1 carbon. Okay, 1 carbon. So the first part of the name is methyl. Then next, I name the acid portion. Acid portion, I have 2 carbon. So it is etanoic. Okay, so instead of oic, it's actually oil. Sorry, can you add an O there? So the name of this ester is methyl ethanoic. Okay, and what is the and this group here is known as the ester linkage. Okay, so the crucial thing for you is you know how to split it out into the acid part and the alcohol part. Okay, can you draw and name the ester formed by propanoic acid and ethanol, as well as fill in the table of esters and its starting material? Okay, so how do I uncover what is the alcohol and carboxylic acid based on the name? Note that the front part here, this is from the alcohol, and the next part is from the acid. So I know that my alcohol has 2 carbon based on the ethyl name. So I know it must be ethanol. And propanoic means it's propanoic acid. Okay, should use it. Methyl ethanoic, again methyl is the alcohol, so methanol. Ethanoic acid. Propyl methanoate, so it must be proper 1-nol and methanoic acid. Methyl decanoate means it's methanol and decanoic acid. What's deca? It's 10. Okay, so butanoic acid plus propanol. How do I name their ester form? Again, we will name the alcohol first. So it is propyl butanoate. Then this is ethyl ethanoate. Then here we have butyl methanoate. Okay, next part. Let's talk about the use of sulfuric acid in this reaction. What do you think sulfuric acid is used for? Okay, there is actually 2 roles of concentrated sulfuric acid in this reaction. First, it is to be a catalyst. Now, this part in brackets, you don't need to know it in detail. This is just some additional stuff. that you learn in JC, but we will not test you on this in secondary school. Okay, so just know that it's a catalyst. Exactly how it works, you don't need to know. Then it's also a strong dehydrating agent. Now recall, when did we see corn H2SO4 as a catalyst before? Okay, it was used in the dehydration of alcohol to form alkenes. So what H2SO4 acts as is also a dehydrating agent. Okay, now if I were to keep removing water from this reaction, you will note that you will drive the equilibrium to the right hand side to compensate for the loss in water. That will increase the yield of my ester. Okay, this is in your equilibrium. Okay, so when we remove water to compensate for this sudden decrease in the concentration of water, the equilibrium shifts to the right, and because equilibrium shifts to the right, it results in a higher yield of ester. Okay, next part on preparation of esters. This part you don't really need to know it in detail. You just need to, okay lah, I shall stop here. I'll go through this in class next week. So thank you, class.